Hello everyone, and as this slide says, welcome to the tutorial on large language models. So we are not going to talk about AI today, since I believe all three of us are a bit skeptical about using this term. So we will be talking about large language models. And specifically, the purpose of this tutorial is to sort of to present large language models not as mysterious black boxes, but to show, what is really under the hood of modern LLMs. And the most important thing, to give you the opportunity to actually play and experiment with large language models which are open, not proprietary black boxes. Right, so the tutorial will be composed of 3 parts. We are now at the first part, where I will introduce the basic concepts of supervised machine learning and deep neural networks, the concepts which are necessary to move on to the second part, presented by David. So the second part will start at 2 sharp, I hope. This part will be dedicated to generative language models per se, so the models which will use the concepts from the first part. All right, modern large language models are based on deep neural networks, on deep learning. And deep learning, in turn, is just a type of machine learning, of supervised machine learning. And supervised machine learning is basically just finding models which allow us to basically find ways to make predictions. Like in this example of making predictions on a data set with instances belonging to 2 classes, blue points and red points, right? So the input of a model is some set of training instances, for example, email messages, which, in the first tutorial today, a task of spam detection has already been mentioned, so let's just talk about this task, for example. Right, so we have email messages as the input instances, and then we have some corresponding gold labels for every message, for every instance. For example, whether this particular email message is spam or not, right? We want a model which will allow us to make predictions for unseen instances. For instances, email messages which we haven't seen during the training. Right, so that's like the general concept of supervised machine learning. And it's important for us because, as we will show later today, any language model is also, in fact, a type of supervised machine learning model. Right? So we need some program, basically, to map instances to labels. Right? So we can design lots of models with lots of different assumptions in mind. So if we have a data set like this, where you see that the instances belonging to the blue class and to the red class are sort of interspersed with each other, right? And then we can devise a model with a decision boundary like this. So very intricate, very crazy decision boundary. Or we can create a model which will be sort of more general, which will devise a decision boundary like this blue circle, or it's not really a circle, right? This weird shape. Or we can decide that we are fine with a model which defines a decision boundary, which is basically just a straight line, like this yellow line, right? And this is the most simple, like the simplest, the most straightforward hypothesis class for supervised machine learning. So a hypothesis that we can separate classes using a linear function, right? It's very simple, it's very straightforward, and it's often enough to solve a practical task at hand. Yeah, I will not dive deep into intricate details. So if you want to really spend time on studying linear functions, you can download the slides. So these are all excerpts from the deep learning and natural language processing class which we are giving at the University of Oslo. But yeah, just in general, any supervised machine learning model which is using linear function is basically just an equation like this one, equation 1, where we have some input feature vector x of dimensionality d in, right? So this dimensionality defines the number of features that we have in the input instances. For example, input instances, if input instances are email messages, some documents, then we are describing these instances using some properties of these documents, some properties of these messages. These properties are features, and number of features defines the dimensionality of the input vector, right? We multiply this input vector by the matrix W, which is basically which basically contains the parameters of our network, right? The parameters of our model, right? And then we add the so-called bias term, right? And the result of this multiplication and addition is the prediction of our model, right? This prediction is a class, right? To train such a linear classifier, right, we need to find like the optimal set of parameters of the model. And the parameters of the model are basically this matrix W and the bias term B, right? So we need to find what values, what numbers should be in this matrix and in this bias term so that they are optimal. And what does it mean to be optimal in this case? It means that the model which is using these parameters will produce predictions y hat, which are closest to the correct predictions, to the goal predictions, right? On some testing instances, right? In the ideal case, we want a model which always predicts 100% correct labels, right? If we have a binary classification, like classification into two classes, like whether the message is spam or not, W is actually not even a matrix, it's a vector, right? So it's just a one-row matrix. And B is a scalar, just a number, right? So the prediction, y hat, will also be a scalar, either 1 or -1. A spam message, not a spam message, right? In fact, the model can output any number, of course. But for simplicity, we will just convert all negatives to -1 and all positives to +1 using the so-called sign function, right? Yeah, so this is the plot, the depiction of such a binary classifier, which takes as an input some feature vector and predicts 1 or -1. So class 1, class -1. Sometimes we want multi-class classification, and this is all sort of leading us to language models, in fact. Sometimes we need a multi-class classification where we have more than 2 classes, not just spam, not spam, but for example, spam, not spam, and maybe spam, right? In this case, we can, for example, solve a task like which languages appear in this document. So what languages are there, right? And then W is a matrix, not a vector, but a matrix now, a table, right? And B is a vector, not a scalar number anymore, but a vector, right? But the equation is still the same. We're still multiplying the input feature vector X we multiplied by the weight matrix W and add the bias term, right? But then, so the prediction is now not a scalar, not a number, but a vector, right? A vector which corresponds to the languages. So which language, whatever language is the correct language of the document. So this component of the prediction vector will have 1 as its value, and other components will have 0. In the fortunate case that our model works correctly, right? So graphically we can represent it like that, right? So so again we have an input feature vector x multiplied by w, which is a matrix, add bias term, and then we just take whatever component of the prediction vector has the maximum value. So this is our prediction. In this case, the prediction is class free, or for example, the language free. Right? Sometimes we can also care not only about what is the correct class, but also how probable this class is. So how confident our classifier is about its decision. So we might be interested not only in what is the correct language of this document, but also how probable it is that the language of this document is, say, English or Norwegian. Right? In this case, we can take the prediction of the model and somehow map it to the range of from 0 to 1, right? By using, for example, some squashing function like sigmoid. So any function which takes as an input numbers from -infinity to +infinity and maps it to the range of from 0 to 1, so that we get the probability, right? This gives us the probability of the prediction. So we have a classifier which can tell us, yes, I'm 99% sure that the language of this document is Norwegian. And if this classifier is at the same time a multi-class classifier, right, we get the probabilities for all the classes, for example, for all the possible languages, right? So we can have a document which is like, there is some probability of this document being in Norwegian, some probability of this document being in English, etc., etc. So this is a classic task of language identification. And then, yeah, we can either choose the one class, the one language with the highest score, or sometimes it's more convenient to convert this prediction of the model into a probability distribution by using a for example, softmax function, right? So then we just have a vector where all the components sum to 1, right? Again, this is the depiction of such a supervised machine learning model. And again, this is, in fact, very useful for language modeling, because any language model, as we will be showing today, is in fact secretly a classifier, right? So it tries to predict which word should be chosen next from some closed set of the words which are known to the model, right? And for this, we need to predict the probability distribution. So we need to output a probability distribution over all the words in the vocabulary, right? So this is like the foundation which underlies all the modern large language models, including ChatGPT, Claude, etc. Right. Let's move on to the so-called neural networks. Right? So again, for like an intermediate summary, supervised machine learning, we want to find the optimal values of the parameters of the model, right? To find the optimal theta. And we are doing this by minimizing the loss while we are training. And the loss, just without, again, going into much details, loss is basically just a measure of how far away the model predictions are from the correct predictions. We can use lots of different loss functions, but one of the most one of the simplest ones is the square error, where we basically just check what is the distance between the prediction and the correct answer, and then take square of it, right? Then we average this loss across all the training examples, and this gives us the estimation of how fit the model is to the data. So this is the measure of how good the model is, how fit it is to the training data. And then we just want to find the set of parameters, basically this matrix W, which I mentioned before, which minimizes the loss, right? Which makes it so that the model has the lowest loss possible. Okay, now we can measure the model performance, right? But the question still remains, okay, we have a model which is sort of randomly initialized with some random numbers in its, as its parameters. How can we actually change these parameters for the model to improve? We cannot do it by hand, right? For this, we're using so-called optimizing with the gradient, right? So that's, this is an optimization problem. We have a set of numbers, a set of parameters, and we want to find, like what values of these parameters lead to the lowest loss, right? So the gradient methods, again, of course, we do not have time to cover them in great details today, and some of you probably already know about stochastic gradient descent, etc. So we don't want to repeat it too much. Yeah, but basically, we just compute the gradient of the parameters with respect to the loss and try to find, like, in what direction we should change the parameters of the values of the parameters of the model so that the loss decreases. Yeah, so we just move all the parameters in the direction which is opposite to loss increasing, right? And we repeat it until we find some optimum value, right? It's important here to distinguish between the so-called convex functions and non-convex functions, right? So since our machine learning classifiers are basically functions, right? Some of them are convex in the sense that they have some single optimum point, some single set of values of their parameters, which is the best one, right? The single sort of point which we want to achieve. But some functions are non-convex. They have multiple optimum points. So yeah, let me just, like in this example, right? So the convex function, as you can see to the left, it's easy to optimize such a model, right? So you can more or less easily find the position in this surface which is like the lowest, right? But if your function looks like the one to the on the plot to the right, then you might have issues with getting stuck at some local optima, right? So you have these saddle points, etc. And yeah, with the linear models, like the ones that I have mentioned before, the error functions are usually convex. So it's really easy to optimize them using gradient methods. With nonlinear models, like the ones used in deep learning, in the so-called deep learning, and in modern large language models, the error functions are usually non-convex. This is some sort of a problem, but in practice, the gradient-based optimization methods still work okay-ish. Right. Okay, so linear models, right? They're great, they're efficient, they're effective, they are easy to interpret. So we have already heard today about interpretability and explainability. Linear models are great in that it's really easy to interpret them because you can usually find the most important features by simply looking at the weights, right? So you can really look at the parameters of the model and sort of find which features are most important or why the model made this decision to some extent. They are still used in many practical purposes, but unfortunately, since these models are linear, they can only handle linear relations in the data. They can only handle classification tasks which deal with data sets which are linearly separable. So the question is, but is it really a problem? Are there some nonlinear data sets, some nonlinear functions that linear models can't deal with? And the answer is yes, there are. Even quite simple functions, like, for example, this excluding OR, XOR function, which is like the textbook example of a nonlinearly separable data set. So you can see that we have some data points which are represented by two features on the horizontal axis and on the vertical axis. And they belong to two classes, red circles and black stars. You can see that however you try, you cannot design a linear decision boundary which will separate these two classes, right? So no straight line can give you correct decisions on what points belong to the red circles class and what points belong to the black stars class. So this is an example of a dataset which is not linearly separable. You cannot use linear functions or linear classifiers to make predictions for this dataset. And many real-world problems are examples of such like non-linearly separable datasets, right? So in order to solve this dataset, in order to devise a classifier which will be able to make correct predictions on datasets like that, we can somehow transform the input. So we can somehow transform the representations of the instances in this dataset so that the dataset becomes linearly separable. For example, just out of your head, you can, after some experimentation, you can find out that if you apply this function on the slide to this dataset, x1, so the first feature becomes x1 plus x2, and the second feature becomes x1 times x2. So if you if you transform all the data points, all the instances in this dataset using this function, then the dataset becomes linearly separable. So the problem is solved, right? We can now define a straight line, which is a classifier, right? Which will be such that all the black stars will be on the one side of the decision boundary and all the red circles will be on the other side of the decision boundary. You can check it yourself afterwards if you don't believe me, for example. But of course, the problem is that it's time-consuming to devise such transformations manually, right? And it's not scalable. We cannot just sit and think how to transform our data sets for every task at hand. So how do we do it? How do we do that? The idea is that we can leave it for the algorithm, for the model itself, to train, like to learn some suitable representations of the data, some suitable mapping functions. So we can leave it to the model to find how exactly the data instances should be transformed. And this is done using multiple layers, which I will cover later, and nonlinear activation functions. So this is basically the idea behind deep neural networks, right? So we want a model to learn which transformations to apply to the data, right? And the transformations themselves are also learnable parameters, right? Yeah, so this equation on the slide basically defines the simplest neural model in the world, the simplest machine learning neural model in the world, multi-layer perceptron, right? So basically it looks very similar to a linear model, with the exception that we also apply some sort of a non-linear activation function G. I will talk more about non-linearities in the next slides. Right. So again, just maybe a more familiar image of a neural network. So this is a so-called feed-forward neural network, or perceptron, with the two hidden layers, right? And conceptually, again, without going into much details, the idea of perceptrons, of feed-forward neural networks, is basically that the input data goes through successive transformations at each layer. So we apply some transformations, like the one that I mentioned a few slides before, to our input data. And the transformations themselves are linear, but after each layer, we have some non-linear activation function, which sort of makes the trick, right, and transforms the data so that if some transformations are needed to make the dataset linearly separable, then these transformations will be learned, right? And at the last layer, we are producing the prediction, as in the case with the linear models, right? And All of this is trained end-to-end, is trained simultaneously, right? So the representation functions and the classifiers themselves, right? And it was shown a long time ago that such functions, neural networks with hidden layers, in theory, can approximate any function. So they are universal approximators. Of course, the question still remains about like whether some specific function can be approximated in finite time. But yeah, still in theory, deep multi-layered neural networks with nonlinearities can approximate more or less any function. Right. Yeah, and by the way, this is what Alan Turing sort of predicted more than 60, 70 years ago. Yeah, so machines of this character can behave in a very complicated manner. So in a very complicated manner is a large underestimation, I'd say, but still. Yeah, and just a short, maybe almost off-topic slide. Why neural networks? Why do we even call such models neural, right? When in fact we know that they're just cascades of mathematical transformations. So why do we call them artificial neural networks? Because at some point people thought that neurons in human brain act somewhat similarly, right? So neurons in our brain are also connected into some large network. Each neuron accepts some electric signals, inputs from other neurons, right? It somehow processes these signals, weighs them differently depending on their source, depending on from what other neuron these electric signals come from. And then it passes its own signals to other neurons. And then, yeah, it all works like some sort of a network, right? And yeah, depending on what is the strength of the input signal, a neuron can be more or less activated. Again, of course, this is a very sort of strong simplification of how our brain functions, but that was the idea back then, at least. Yeah, and yes, the whole system is also distributed, which is also the property of modern artificial neural networks, right? So the knowledge sort of about the task at hand is distributed across the whole system. Yeah, but I'd say that although originally, indeed, artificial neural networks were based a lot on our knowledge about how human brain functions, but since that time, I'd say, yeah, we have moved very far away from neuroscience. And in fact, yeah, it's less cool but more convenient to talk about artificial neural networks in terms of linear algebra concepts, in terms of vectors, matrices, algebraic operations on these vectors and matrices, instead of talking about neurons, electric signals, etc. So that's why, yeah, although of course it sounds very cool when we're talking about models which function like brain, but I think it's much more useful to actually talk in mathematical terms. Right, so again, let's get back to math. So in fact, this plot is already a simple neural network with one neuron or with one computational unit. So a neuron is a computational unit, right? It's some point in which we conduct some computation. So in this case, the input is a feature vector of dimensionality 4, right? So we have some training or testing instance which is described by 4 features, right? And we have a vector of weights corresponding to each of these features. So this vector is called W on this plot. Yeah, so we have weights W1, W2, W3, and W4, right? In the simplest case, this neuron is basically just a weighted sum of the inputs, right? So we take feature 1, x1, multiply it by the weight W1, then we do the same with the rest of the features, and then we sum this. And this is the output of this neuron, right? So this is a very simple neural network. Not very useful, but it's enough like to show the concept, right? Yes, so the output value is basically just a weighted sum. In fact, we can sort of populate this abstract graph with some real world task, like for example, sentiment analysis. So let's imagine that we want to predict whether some sentence is positive or negative, some English sentence is positive or negative, based on the fact of whether the sentence contains words like fun, great, long, and boring. So yeah, if a sentence contains such a word, then the corresponding feature has the value of 1. If it doesn't, then the corresponding feature has a value of 0, right? And we have a weight matrix. So in this case, you can see that the weights in the matrix W are 0.5, 0.5, minus 0.5, minus 0.5. So if we have an input instance which contains a word long and contains the word boring, but doesn't contain the words fun and great, then if you take the weighted sum of all these inputs, the output will be -1, which will correspond to the negative class in this task. So as you can see, in fact, even such a simple one neuron perceptron can already be used to solve some real-world task. Right, but of course, in reality, in practice, our artificial neural networks are usually much deeper and much wider. So they have much more layers and much more neurons in each layer. So like in this case, where we have an artificial neural network with 6 computational units in the first hidden layer and 5 computational units at the second hidden layer, and 3 computational units at the output layer, which means that it predicts 3 classes, so to say, right? So yeah, we can also call it a stacked linear classifier, right? Because each of the layers is basically just a linear classifier, right? And we stack them. So that's why I mentioned the word cascade in one of the previous slides. So this is a cascade of linear classifiers. Unfortunately, any stack of linear classifiers is still a linear classifier. So this thing still will not be able to solve data sets like exclusive or other nonlinear problems. That's why we're using these nonlinear transformations or activations that I mentioned before, right? And they are actually the core reason behind all these recent successes of deep learning, including in natural language processing and language models. So the usage of these nonlinear transformations was really one of the key revolutions in using artificial neural networks, right? So these nonlinear transformations help to induce like good input data representations, as in the example in one of the previous slides where we transformed the input so that it becomes linearly separable, right? So that's why we need this. And then, yeah, once the data is transformed in such a way that it is linearly separable, we're using a simple linear classifier in the end, right? There are dozens or maybe hundreds of activation functions, but some of the most popular are, for example, sigmoid, then a very simple function which is called rectified linear unit, and it's really simple, and I mean it. If you look at the equation, you can see that it's basically just you have an input x. If x is positive, if it's more than 0 or 0, then the output is equal to the input. If the input is less than 0, for example, or 0, then the output is 0, right? So this transformation is nonlinear. It's very simple. It's very computationally cheap, and it does its job, right? You can also think about other transformations like hyperbolic tangent, etc., etc., etc. So the main trick is that you want this transformation to be nonlinear. So it shouldn't be just a linear transform. Right, so this plot shows a deep neural network And the only difference between this deep neural network and the stack of linear classifiers are non-linearities between linear transformations. So once we add non-linear transformations, we are now in the realm of real deep learning, right? Yeah, so just again, to sum it up, the input data in deep neural networks goes through successive transformations at each layer. The transformations themselves are linear, but they're followed by some non-linearities, by some non-linear activation functions at each layer, and they can be different at each layer. So some architectures use different non-linear transformations at each layer. And at the last layer, we produce the prediction. Right. So that's your deep learning system. Such architectures are sometimes called feed-forward neural networks. So that's a more precise name for a multi-layered perceptron. So it means that the neurons, the computational units in the network, are connected to each other without cycles, right? And they are all fully connected in the sense that each neuron in the previous layer is connected to each neuron in the next layer, right? Yeah, which makes it very simple, because basically every next layer is just a multiplication of a vector by a matrix, and that's it. Right? Some neural architectures are not fully connected, not feed-forward, so some do use cycles, etc., but we're not talking about these architectures today. Right? Yeah, so just some recap on terminology. The first layer contains input units, right? The input features of what we feed to the network. And then the last layer contains output units, the predictions of the network. In the simplest case, classes, the probabilities of the classes. And the layers in between are called hidden layers. They contain the so-called hidden units. And they form hidden representations, right, of the input data. Right. So again, this is still just a machine learning classifier, which consists of some set of parameters in this matrix W and in the bias term. So the parameters of the network are what people are talking about when you hear them talking about the model size, right? So when you hear about, I don't know, Meta or Google having released a new model of size 400 billion parameters, it basically means that their W matrix has 400 billion cells in it. Right. So the aim of the training, again, is just to learn the optimal values of the cells in this matrix. Or, yeah, you can say that it's just a set of matrices. Unlike the linear classifiers, in deep neural networks, the error function is usually not convex. But again, as I've said, gradient-based optimizers like stochastic gradient descent, ADAM, etc., still work well. So they're still being used to optimize deep neural networks. And yeah, of course, if you are training like your own model, your own artificial neural network model, you can try to balance between the width and the depth of the network. So try to balance between the number of layers and the size of each layer. Right? So sometimes these decisions can be very crucial. Right? Yeah, and yeah, it has been shown a long time ago that different layers learn different hidden representations. And yeah, this sort of eliminates the need to manually design feature combinations. So in the past, like 15 years ago, people in natural language processing were really busy with manually designing features like if we have the words not and good in the sentence together, then it's probably a separate feature of its own, on its own, and it was all very time-consuming and not very efficient. But nowadays, with deep neural networks, we have models that are able to learn themselves that the fact that the words not and good occur in the sentence is a feature which should be taken into account, right? Something is not good. Yep. So the deeper and the wider the model is, the more parameters it has, the more complex functions it can approximate, the more powerful it is. And yeah, it's very easy to visualize. Like in the plot to the left, we have a model which has only 3 hidden neurons, only 3 computational units, and the decision boundary that it can define looks like that. It's quite simple, as you can see. But in the plot to the right, a model with 20 neurons with 20 computational units can define much more complicated decision boundaries. And to solve real-world tasks, like, for example, creating a chatbot which can really talk to you, you need very complex decision boundaries. Right? Yeah, and just the final part of my talk will be about the one god of modern large language models, the transformer architecture, right? So the architecture which powers almost all modern large language models, and even not only language models, but also computer vision models, text-to-image transformers like DALL-E and Stable Diffusion, etc. So almost all of them invariably are based on the transformer architecture. It started with now almost forgotten BERT model, which was a revolution back then in 2018 when the BERT paper was published. So now we're in the era of GPT models, which are also based on the transformer architecture. So the letter T in the GPT abbreviation is transformer. Right, but there are also many other models and architectures which are based on transformer. So what is again? Of course, I'm not going to cover all the details of the transformer architecture. You can follow the links in the slides for more in-depth descriptions. But the key feature of transformer, conceptually, transformer is still a feed-forward neural network. It's still just a succession of fully connected layers, which sequentially transform the input until you have the output. But like the most important thing is that transformers introduced the thing called self-attention, right? So the way for the model to learn the relative importance of tokens or words in the different positions of the input. So that's the citation from the paper by Vaswani et al. 2017, which introduced the transformer architecture. Back then, they used it for machine translation. Since then, it has been used for, as I have already said, for almost any imaginable natural language processing, and not only natural language processing task in the world. And the very important thing is that back then, when transformer was introduced, the dominant neural architecture was recurrent neural networks, RNNs, LSTMs, etc. And they were good, but they were not very parallelizable. So they were not very efficient to run, to train, to compute, right? Unlike recurrent neural networks, transformer is fully parallelizable, and it makes a very good use of modern computational hardware that we have now, GPUs, TPUs, etc. So this was one of the decisive sort of breakthroughs that actually allowed to train really efficient models and to do it in more or less finite time spans. So yeah, this picture, I believe that all of you probably have seen it at some point. That's the plot of the transformer architecture. Again, without going much into details, you still have the input, which is basically just like some set of words or sub-word units in the case of natural language processing tasks, and the output, which in the case of language models will be just the probabilities of the next word, which should come after the previous words. Yeah, so again, this is from the original transformer as it has been used for machine translation. So in machine translation task, you have the input which is in one language and the output which should be in another language, right? So that's why the original transformer architecture used several encoder layers which are employed to sort of to produce an efficient representation of the input, say of a sentence in English, right? And then it uses a cascade of the so-called decoder layers, which are used to then generate a sentence, a document, a text in the target language, say in Norwegian, right? So the original transformer architecture consisted of like two parts, encoder and decoder. And in fact, since then, like there exist like three major types of transformer architectures, or three applications of attention in the transformer architecture. The encoder-decoder way, the encoder-decoder approach, where, yeah, we first encode the input and then we decode the output, which is a natural text or an image or whatever. Then we have the second type of the transformer architecture, which is encoder only, where we take an input and then we produce some vectorized encoded representation of this input, right? And finally, we have the decoder only models, which basically, yeah, just attend to all the previous positions in the input and decode the output. These are also called autoregressive language model, right? Autoregressive modeling. And today, we will mostly be talking about these types of models. So all these large language models which you are dealing with when you are talking to ChatGPT, Claude, etc., are basically autoregressive or decoder-only language models. And in the hands-on session today, you also will be dealing with decoder-only autoregressive language models for Norwegian. Right. So yeah, that's you can look at this slide later. It's just a table from this seminal paper by Vaswani et al., which shows how good transformer used to be for machine translation back then in 2017. So it was better than its competitors at a small fraction of the training cost. But yeah, not long after 2017, as I've said, transformer became really the dominant architecture for language models, natural language processing models in general, and artificial intelligence in general. So again, to conclude, almost any so-called AI model in the world that you can find nowadays, including language models, will be based on this or that variation of the transformer architecture.
Welcome to the second part of this tutorial. And yeah, first of all, I should just say that I have only 45 minutes to cover the large language models. So this necessarily means that I will try to cover a lot of topics, but I will not get into much depth. And also, it might be a little overwhelming. So please, if you get lost anytime, just raise your hand and ask questions. Or if you just want to explain something in more depth, it's also okay to just stop for a bit and go more into it. We don't necessarily have to finish everything, right? So, okay, so let's start. I will start with just introducing what actually language models are. So language modeling is a very old concept, actually. It was introduced back in the 1940s by Claude Shannon. And basically, as the name suggests, language models model language. They are the statistical models of language that try to estimate the probabilistic distribution of language utterances. And we estimate these probabilities by having a look at a very large corpus. And this corpus is typically a collection of books or newspapers, transcriptions of movies, and nowadays typically also corpora are big collections of web pages scraped from the internet. So we have a very huge sample of our natural language, and from this sample, we estimated the distribution of these language utterances. And we can have a simple example now, where we don't have this large corpus here. We just have a very, very simple corpus of just 10 symbols. So in our language here, we have only an alphabet of 4 symbols. And from this corpus, we can already estimate something, right? So we can have this very simplest language model that there is, that just, estimates what's the probability of the symbol A. And as you can see, there are 4 occurrences of this symbol in our corpus out of 10 total symbols. So we can say that the probability of A is 40%. Similarly, probability of B is just 30%, C 20%, and probability of D is 10% because there's only one occurrence of the symbol D. So yeah, that's pretty simple, right? We can get slightly more complex and have a look at the conditional probability. So what's the probability that symbol C follows the symbol A? Well, if we have a look, we have A that follows A, B that follows A, then again B that follows A, and one example of C that follows A. So one of the 4 examples is C following A. So the probability of C following A is 25%. And similarly, we can estimate the probability of C following A and B. Again, there are two occurrences of A and B in our simple corpus. One of them is followed by C. So the probability of C following A and B is 50%. Yeah, so this is basically language modeling. And generally, we can, just by having these huge tables of conditional probabilities, we can then estimate the probability of any kind of sequence of symbols, or in our case, words, by using this chain rule. We factor the probability into these products of conditional probabilities. So for example, the probability of A, B, C, right after each other, is equal to the probability of A times the probability of B given A times the probability of C given AB. And we could basically end the slides right here, because, this is language modeling in theory. You could just have larger and larger tables with bigger and bigger conditional probabilities. And just by doing this, you would have a perfect language model, actually, much better than all of these GPT models and whatever. And if someone says that language models are the path to artificial intelligence, by doing this, you would have this super artificial intelligence. But there's one very big problem with this. Can anybody guess why we can't really do that? Sorry, can you speak up a bit? Uh-huh. That's one of the problems, but usually we just solve it by taking the logarithm of the probability and then just summing up the log probabilities. So we get rid of this numerical issue. But we actually use this chain rule also with the modern transformer-based language models, and you will see this later. So this is not really the problem that is there. There's a different problem why we can't do it in practice. So the problem is actually that these conditional tables get really, really big very quickly. They scale exponentially. So if you have an alphabet of V words, the size of this conditional table is V to the power of the number of symbols in it. This just goes up very quickly. So we can't estimate the probability of more than, I don't know, four words right after each other in practice. But we need to estimate the probabilities of sequences of length 2,000 or 10,000. So we can't do this. Fortunately, there's a solution, and that's why the first part talked about deep learning, because we can simply approximate these huge conditional tables by using deep neural networks. Specifically, in our case here, we will use the transformer neural networks to approximate these. So, so the task of these networks will be to approximate these intractable probability tables that, on the input, these models will have a sequence of words, and they have to estimate what's the probability of the next word, what's the probability distribution of these, And how does it work? Well, it works because language is not totally random, right? Language has some kind of structure, and these transform-based language models can see the patterns inside, and they can be very good at sort of making sure that even though they are relatively small compared to these exponentially large tables, they can still estimate these probabilities very well. But maybe you're now asking yourself, okay, we can estimate the probability of a sentence. Like, what does it even mean, and how is that useful for anything? It is very useful, and we will use this not to actually use these probabilities by themselves. We will use this to solve some kind of tasks that are in the NLP. So, for example, we could solve it, use these language models to solve the sentiment analysis task. So, you have already seen an example of this previously. So, given a sentence, is the sentiment positive or negative of this sentence? So, in the old school machine learning that you saw in the previous slides, we just don't have any language model. We just have a very smart engineer that engineers the features out of the sentence. So, for example, does the word good occur in the sentence or not? And then we train a supervised model based on this. This is the sort of old school machine learning approach, but more modern approaches use the fine-tuning and prompting. We'll mostly cover prompting, but let me just quickly talk about fine-tuning. So with fine-tuning, we use the language modeling just as a proxy. So when we train this huge neural network on language modeling, it's just this kind of unlabeled task where we can use huge amounts of data. And by estimating what's the probability of the words, the language model has to learn a lot of things. It has to learn about the language, it has to learn its grammar, and it has to also learn a lot of knowledge, a lot of word facts. So, for example, if we have the sentence, the capital of Norway is, then to complete the sentence successfully, the language model has to know what's the capital city of Norway. And so then with fine-tuning, we do this kind of pre-training of the language model, and then we use the weights of the language model as sort of initialization for the next task that then uses all this knowledge. So this is the two-stage approach where we first pre-train the model, and then we fine-tune this model on some kind of supervised task. Now, we will not have time to talk about fine-tuning that much today, but we will simply talk about prompting, where we totally skip this fine-tuning stage, and we just use the language model itself. Even though the language model has never been trained on a supervised task, we will use it as a supervised model, kind of, to solve a task. And this might now seem like it's impossible to do, but I will show you that it's actually quite simple later in this presentation. Okay, so let's move to this generative transform-based language models. We will use transformers nowadays, and specifically for these generative models, we will just use this kind of decoder part, as was already covered. So the task of these models is the next word prediction. So given some prefix, estimate what's the probability of the next word, which is basically the conditional probability that we saw earlier. These models have many different names. Sometimes they are called causal language models, or decoder-only language models, autoregressive language models, left-to-right language models, GPT-like language models, or just simply language models, because this has become synonymous with generative language models nowadays. And yeah, the goal is to estimate the probability distribution of sequences of words. So I have just this very abstract illustration of how the transformer models solve this task. So in this image, at the bottom, you just see the input to this language model. And these circles denote the hidden vectors inside the language model that go layer by layer. So you see the hidden vectors at the first layer, second layer, third layer, and so on. And at the end, you can see that each word tries to estimate what's the next word. So right at the left, we have the sort of artificial beginning of sequence symbol. And this artificial beginning of sequence symbol then gets input into the transformer, gets it through the layers, outputs some hidden vector for each layer, and then at the end, it should output the as the next word. And similarly, we then input the beginning of sequence symbol and the into the model, and then it should estimate or predict the next word, which is quick, and so on. And the important thing in this figure are all of these lines that show you what other words each word has access to. So, for example, the first beginning of sequence symbol doesn't have access to any other words. It just sort of sees itself, and it should predict the first word. But then, for example, the word quick has access to all the previous words. So the beginning of sequence symbol as well as the word the. And then based on this information, it should then output the word brown. And sort of this looking into the previous words is what the attention mechanism inside the transformer model does. Yeah, does anybody have an idea why we constrain the model like this? Why can't just every word look into all the other words? Why is there this like left to right constraint there? Yeah, there's a hint. Yeah. Right. Because if you, you can't use the future information because it will be some kind of leakage, right? You couldn't really train the model otherwise, because if the model knew that the next word after quick is brown, if it had access to it, then it wouldn't learn anything. It has to be sort of forbidden from this knowledge to actually learn what's the next word. And so this is actually it, very simply. So the whole task is then just a simple multitask classification, as you saw in the previous lecture. There's nothing very complicated about it. The complicated thing, of course, is the transformer architecture itself, which we don't have time to really cover in detail. But otherwise, the training itself is just multi-class classification, and you just have to make sure to mask out the right contexts from these words. Okay, so quick history of language modeling. So we will not get into all the interesting history before neural networks, but the important part was in 2001, when Bengio proposed to solve language modeling by using neural networks for the first time, and it was a big revolution when he showed that it's possible to actually do that. And many works followed after that, but the important one for us is the first GPT paper, which basically did pretty much the same thing as Bengio, but they just used the transformer model as the backbone there, and they trained it on much larger corpus of data than before and much more compute. And by this, they actually trained a very good language model that then they showed that it can be used for this kind of fine-tuning task, and it performs much better than all the previous approaches. Then, a year later, in 2019, Alec Redford introduced the next iteration, GPT-2, which is basically the same thing, but it's scaled in size. They also then trained on a much bigger corpus than before, also including a lot of web data. And now, for the first time, they showed that they don't only have to do fine-tuning, they can also do kind of well without any fine-tuning, just by using prompting. The big revolution then was GPT-3, which then scaled these GPT models to a bigger size. Again, there was not really like a technical revolution there. They just trained on more data and with a bigger model. But this bigger model then became very good in this kind of in-context learning, which is what we call this prompting, where you don't have any supervised data. You just sort of treat this model as a supervised model. And sometimes you can also hear the term emergent abilities, which describe this kind of behavior when at the smaller sizes, these models are not able to do this kind of in-context learning, but then suddenly, at some point, the performance jumps up, and suddenly the models are very good in doing tasks without actually being trained on these tasks. Now, yeah, that was introduced in 2022. Nowadays, it is slightly controversial because it was shown that this paper was not done entirely correctly. But still, it's a term that you can hear a lot, and it really kind of is connected to this in-context learning and to this sudden jump in performance. Okay, and yeah, and after GPT-3, I mean, nothing that interesting happened for the base language models themselves. We just train them on more and more texts, basically, and they get better and better, and that's the story, kind of. So yeah, let's talk a bit about this in-context learning. So it's very good that now we can use these decoder language models to solve tasks without actually having to annotate any data. But it's sort of double-edged sword, because yes, these decoder-only language models are very good in this, but they are not very good in anything else. And they have to be very big to be good in this. And it's very expensive to train these models, unfortunately. So oftentimes in practice, you then face this decision if you should allocate a lot of resources to annotate a new data set, or if you should just use an existing language model and just infer from it. And yeah, and it's a question of costs, of course. Because the fine-tuning is still a much better thing to do if you want a very good performance, but it can be very costly to annotate a data set. Yeah. And yeah, I'm not sure how visible this picture is, but it sort of shows on x-axis, it shows the time, and on the y-axis, it shows the performance on a MMLU benchmark, which is like a famous language modeling benchmark, which is nowadays used. And it shows the big revolution of the language models, how they got better and better. But there are like these red dots, which dominate at the beginning, and these are the closed source language models. So these are language models like ChatGPT or Claude, which are sort of hidden behind a wall. You don't have access to the weights of these models. If you're lucky, you have access to the API, and you can infer from these models, usually for some kind of payment. And for a long time, these models were dominating, but you can also see the green dots, which are getting closer and closer to the red dots. And the green dots are open source models, which have all the weights available freely, so everybody can just download this model and use it themselves. And it's very important that these models are available, because the scientific contribution of these closed source models is not always there, really, because oftentimes they release some papers, but the papers are more like advertisements, not really any peer-reviewed articles. The models are not released, as well as the evaluation code, so it's impossible to reproduce anything or verify the results. And we also don't have any information on what these models were trained on. So we don't know if there's some data leakage or so, and so on. So fortunately, there are lots of initiatives that try to change that, and that train models openly in some ways. So the first one was probably GPT-J in 2021, which tried to replicate the GPT models. And then we have things like OPT, Llama, Mistral, or Quen. And also important one is Olmo, which tried to make everything public, so the whole training code, data set, and as well as the weights. So now let's move to this prompt-based learning. And how does it actually work, that we don't need any annotated data to perform some task? So first of all, you already saw what supervised learning is. So let me just reformulate it a bit into this formalism here. So in supervised learning, you have a data set of some input and output pairs, and you really learn to assign the correct label Y to any input X. So then your model tries to estimate this probability that the label Y follows the input X. So this is great. If you have a very large annotated data set, you can then learn to estimate this probability. But in practice, you oftentimes don't really have this. But what you can do is you can use a language model. Now, a language model, of course, learned a different probability. A language model learned to estimate the probability of a text sequence T in this case. But we can reformulate the task so that we approximate this probability of label Y given input X by language modeling. And we do this by using some kind of prompt template, F, that transforms the input-output pair XY into a natural text sequence, and then we use the language model to approximate this. So instead of looking at what's the most likely label given an input X, we look at what's the most likely prompt that's transformed from the input pair X and Y. This is probably a bit confusing, but let me show some examples of how it looks in practice. So here we will be solving the task of sentiment analysis again. Specifically, I think it's sentiment analysis of movie reviews. And so as an example of input X, we have the sentence, "I really enjoyed this movie." And we have two possible labels there. We have the label that says that this review is positive, and then another label that says that this review is negative. So this is sentiment analysis. But now we will not really do any supervised learning. Instead, we will do this prompt-based learning. And so we will use this prompt template that transforms these two, this pair, X and Y, into a natural sequence of text. And so with this prompt template, we will first insert the input X into that. Then the text, to sum up, it was follows. And after that, we have two possibilities, either the word good, if the label is positive, or the word bad, if the label is negative. And then what follows is the word movie. And if we insert the actual inputs into there, we get these two text sequences. I really enjoyed this movie. To sum up, it was a good movie. And I really enjoyed this movie. To sum up, it was a bad movie. And we put these two sequences into a language model. And if you have a language model that has some kind of degree of understanding a language, it should assign a higher probability to the first sequence than to the second sequence, because the second sequence doesn't really make sense semantically. And then by doing this, we can infer that the label, in this case, is positive, because the first sequence has a bigger probability. And so this is how we can then transform the task into just regular language modeling. And and so in practice, we just select then the label that corresponds to the text sequence with the biggest probability. So that was a filled prompt, which we can then use for any kind of classification task where we have just a small limited number of labels. Another option of course, is to generate freely some output, which you will need for a lot of tasks. For example, for machine translation or summarization, where you don't really have like a label. We just have to generate some other text sequence. And so for this kind of task, we will use a slightly different prompt called close or prefix prompts. Close prompts are used when you generate a text in the middle of a text. So we will be using the prefix prompts here. And yeah, so here you only transform the input x without actually caring about the output y, because that will be something that the language model itself will generate. So in this case, we will do a machine translation from Norwegian to English. So we have some input x. We have an output y, which we don't really care about right now. It can be any possible correct English translation. And we will use a slightly different prompt that is tailored to the machine translation specifically. In this case, it will be the Norwegian sentence, something inside, can be translated as column, and then the model should generate the suffix of this text sequence. So yeah, when we fill in the sequence, it looks like this. And again, if we have a good enough language model, it should understand that the most likely sequence that follows after this input is actually the translation of the Norwegian sequence. Of course, you also have to have a language model that has seen a lot of Norwegian as well as a lot of English, and also has some kind of translation capability. So probably it has to have some language learning examples in its corpus, or some web pages that have like both versions of language inside and so on, so that it can actually also do the translation. So language model has to do two tasks, right? It has to understand what you actually kind of mean by this prompt, and then it has to also be able to perform the target task. And yeah, so we input this into the language model and generate the output, and if we are lucky, it actually generates the translation. Now, in case of machine translation, we can actually just take this generated output, and we are happy because this is the translation. For some other tasks, we might not be as lucky because we will have to do some other transformation. For example, imagine now that we are doing sentiment analysis here, and we are just generating the target label. Well, the model might generate just positive or negative, but it can also generate a lot of other words like good, bad, or something else, or it can generate a whole explanation of why it thinks it's positive or negative, and so on. So we would then have to use some other heuristic that transforms it into the correct label. So sometimes this can be a bit difficult, especially with the closed source language models, which often only offer you to generate text, and then you have to stick with this kind of approach. You can use this approach that was previously shown, where you just compare the probabilities of different outputs. Okay, yes. So now we should also mention what does it mean, the zero-shot and few-shot learning, which you often see associated with prompt learning. So the two examples that I have shown you were examples of zero-shot learning, where we have no supervised data at all. We only give a prompt to the language model, and we expect it to complete the task. But usually it's not very hard to come up with some examples of the correct behavior with some supervised data. And then we used few-shot learning, where we actually show the model like a handful of examples of the correct behavior. And this, of course, makes things much easier, because it can sometimes be hard to infer what do we actually mean by our prompt. The language model can just very easily diverge to some other direction and not really complete the task that we wanted. But by including some demonstrations of what are the correct outputs, the model can then follow this pattern and complete the task successfully. So yeah, so we include some examples of the input-output pairs in the prompt itself and show it to the model. Yeah, that's it. And so this is an example, again, sentiment analysis. But in this time, we will not use as complex prompt template as before. because now we will show it 3 examples of the correct behavior, and then we will hope that the model will follow after that. So yeah, so again, we have like a review, which is the input. We have 2 possible labels. But now in our prompt template, we will show 3 demonstrations of the correct completion of this task. So we have an input, then like this arrow, and the correct label. Then we have another input and another gold label. And then another input and another gold label. And then we insert a new review, and we hope that the model can pick up this pattern and generate the word positive or negative, because it sort of understands that, yeah, this is the most likely sequence that follows. So this is the example of the filled prompt, and then the model should just generate the label negative or positive. And this is an example of this 3-shot prefix prompt. Okay. Yeah, we have like 10 minutes. So yeah, we can talk about how do we actually do generation. So we have learned what language models are. We sort of learned how they are trained. We learned how they are used, but we still don't know how actually they generate text at all. So let's now quickly go through that. And if you remember the picture I showed you earlier about how we actually train these language models, this is it's very similar to how we then use them during inference to generate something. So as the first step during generation, here we just will generate from scratch, but you could also put like an existing prefix into the language model. But here we just put like this special beginning of sequence token into the model. And yeah, we put it there. It gets through the transformer. It gives us the probability distribution of the next word that follows this special token. And now we somehow pick one of the tokens from this distribution and put it into the input again. Now the input is the special beginning of sequence token, and again we will move through the layers of the transformer and have a look at the final distribution that shows the probability distribution of the third word. We will pick one of the tokens from this distribution and again put it into the input, and again look at the output. We will put the output into the input and do this iteratively until we generate the full sequence. Right? So now the only question is, how do we pick the output from the distribution? There are two ways how we can do it. We can either try to search for the most probable sequence, or we can do it by random sampling. So I'm not sure we have time to really go into details here. So I will probably go very quickly here. So again, searching for the most probable sequence is very hard. It's again exponential, so we can't really do it. So we simplify things a bit. So yeah, here you can see the problem. So after the special token, we have 3 options what can follow if we have just 3 symbols in the alphabet again. And then after that, you see that it multiplies to 9 options for 2 symbols. And then for 3 symbols, it again multiplies by 3. So this is exponential, and we would have to look at the probabilities of all of these options to search for the best one, and that's just simply intractable. So what we are doing to do this is that we use this sort of so-called beam search. When we restrict the possible sequences that we look into just a small number of them, in this case, we will constrain this to just 2 sequences at a time. So we start on the left by this special S symbol, and then we have 3 symbols after that. And we just pick the 2 most likely out of these 2. Then again, for these 2, we will again consider all the possibilities that follows after that. So these are 6 different sequences. And we see that the 2 most probable out of them are the CA and CB sequences. So we again constrain us just to this 2, and again have a look at what are all the possibilities of the next symbol. Again, just pick 2 and so on. And by doing this, we now moved away from this exponential complexity to just simple linear complexity. Of course, now it's just an approximation of the most likely sequence. We will not get the actual most likely sequence. But this is usually good enough. Yeah. And yeah, so this is how we estimate the most probable sequence. But oftentimes in practice, we simply reduce the beam size to just 1. And this is a special case that is called the greedy search. And what this basically means is that when we look at the probability distribution of the next word, we just pick the one most likely token and totally don't care about anything else. So then we have the beam size of 1, and it's the greedy search. It's very simple. And if you have a big enough model, it actually gets very close in performance to the full beam search while being much simpler. So this is what people nowadays quite often use. Yeah, this searching for the most probable sequence is good, but it's often not what we actually want. And as Holtzman said in this paper, natural language does not maximize probability. You probably notice that when people talk, they are not robots. They sometimes say something unexpected, surprising, interesting, not just the most mundane things that follow one after each other. So when we have a look at what's the estimated probability of text generated by beam search and text that actually generated by actual humans, we see that the humans, the probability of the words by humans is much different. Sometimes, yeah, humans follow the beam search, but other times they just say something totally unexpected out of the blue, and that's kind of what makes the natural text sound natural. So we would like to do this too, and we can do this by random sampling. So the problem with this beam search is that the outputs can sound stiff, generic, repetitive, or just boring. And sometimes this is exactly what we want. So for example, when we are doing machine translation, we don't want the model to just stop doing the translation and tell us a funny joke. We want the model to actually do the translation, which is kind of boring, but then we will stick to the searching for the most probable sequence. But other times, for example, when we are designing chatbots, we want these chatbots to sound more natural. So for chatbots, random sampling is the way to do it. Yeah. And so we do sampling from the output distribution of the next word. Yeah, and we can actually have some control of how random or creative the outputs are by using this parameter called temperature. And I will not go into the technical details, but basically it means that when the temperature parameter is set to 0, the probability distribution over the words just approaches the one-hot distribution, and this basically just then simplifies to simple greedy search when we are just picking the most likely token. But then when we make the temperature higher and higher, the distribution will get more and more uniform, and so the outputs will be more and more random. And so usually there's like a sweet spot somewhere that can be different for different tasks, and you have to tune it. But that's how we can control the random sampling. Yeah. Okay, it's 45. And this is the last slide. So yeah, thank you.